Today we are going to use quantum mechanics for a simple problem where we consider particle bouncing back and forth inside a box. This is usually the first example that are taught in quantum mechanics classes. I will discuss it in detail since if you understand it thoroughly, it will be much easier to understand more advanced examples of quantum mechanics. A particle is bouncing around between the two ends of an impenetrable box. It is assumed that there is no friction, so the particle will keep bouncing back and forth forever.
Also, we assume that the particle moves at a relatively low speed so that we don't need to worry about the relativistic effect. For simplicity, we assume a one-dimensional case initially.
Later we extend the result of one-dimensional case to three-dimensional case. Typically, the classical physics draws the particles that it describes as small spheres like this one. The actual quantum system to be analyzed is shown here like this. Here a particle like an electron has no non-specific shape or size, but it has a wave function blob, something like this. So in quantum mechanics, the equivalent of a particle bouncing around is a wave function blob that bouncing around between the ends of this box. So the only difference is that in classical picture we have a clear position or a clear shape for the particle, whereas in quantum mechanics it tells you that it is not possible to have the exact shape or size. It is not possible to define an exact shape or size. So we consider it as a blob, as a wave function blob, and you don't need to worry about what this impenetrable box is. It's obviously a crude idealization, and you could imagine the particle as a valence electron in a very tiny bar of copper. In that case, the box would correspond to the surface of the copper bar, and it is assumed that the electron cannot get off the bar. The first step in the solution process is to describe the problem mathematically. To do so, an x coordinate that measures the longitudinal position inside the box will be used here. Also, the length of the box in that coordinate will be Lx as shown here. The first step to study any quantum mechanical problem is to find out the Hamiltonian that describes the situation. For this, we need to know the potential and kinetic energies of the system. In this case, we consider the particle as a free particle where it does not experience forces inside the box. Since force is the gradient of potential energy, we can say that the potential energy must be constant inside the box.
Since a constant value does not make any difference physically, we assume that this constant potential has zero.
Now we need the kinetic energy of the system, which is given by p square by 2m, where p is the linear momentum and m is the mass of the particle. If we substitute the operator form for momentum, which is minus ih cross dou by dou x, we get the kinetic energy as minus h cross square by 2m dou square by dou x square. So we can see that the Hamiltonian H is just this kinetic energy since the potential energy is 0. With the Hamiltonian H found, the next step is to formulate the Hamiltonian eigenvalue problem or the time independent Schrodinger equation. And this is always of the form H psi is equal to E psi. This wave function small psi appearing in this equation is a time independent wave function, and it's a function of position alone. Any non-zero solution psi of this equation is called an energy eigenfunction, and the corresponding constant E is called the energy eigenvalue. Substituting the Hamiltonian, which we formulated in step 1, the eigenvalue problem becomes minus h cross square by 2m dou square psi by dou x square is equal to E psi. To completely specify the problem, we need something more, the so-called boundary conditions. These are the conditions that specify what happens at the boundaries. In this problem of particle in a one-dimensional box, the boundaries are the two ends of the box, that is x is equal to 0 and x is equal to Lx are the boundary points. Since the particle is confined inside the box, we expect the wave function only inside the box. Why is it so? This is because the square magnitude of the wave function gives the probability of finding the particle. So the wave function must be 0 where there is no possibility of finding the particle. Since there is 0 probability for finding the particle outside the box, the wave function must vanish at the boundaries. That means psi must be 0 at x is equal to 0 at this boundary and also at x is equal to Lx. In the next step, we try to solve the eigenvalue equation which we formulated in the second step. We can rearrange this equation into a second order differential equation like this one, and if you make a substitution for this 2me by h cross square by some constant, let's say kappa, then the equation looks like this. Now it turns out to be a second order differential equation solving process which you all know.
Now let's explore various possibilities that the energy can have. If you assume that the energy E is negative, then kappa will be having
this particular form, square root of minus 2me by h cross. Then the solution will be like this: C1 e raised to kappa x plus C2 e raised to minus kappa x with kappa defined in this form. This solution may easily be checked by simply substituting it into the ordinary differential equation. As far as the ordinary differential equation is concerned, the constants C1 and C2 could be any two numbers. But here in quantum mechanics, we determine the values of these constants by applying the boundary conditions. So C1 and C2 have to satisfy two boundary conditions we have just seen in the previous slide. First boundary condition, that is psi is equal to 0 when x equal to 0, produces C1 e raised to 0 plus C2 e raised to 0 equal to 0. So what we did is you simply put x is equal to 0 in this expression. Then this will lead C2 equal to minus C1. Now we apply the second boundary condition, which is psi is equal to 0 at x is equal to Lx, and this leads to the expression C1 e raised to kappa Lx plus C2 e raised to minus kappa Lx is equal to 0. But since we have already seen that C2 is equal to minus C1, this equation can be written as C1 into e raised to kappa Lx minus e raised to minus kappa Lx is equal to 0. This equation troubles us because the term between the parentheses cannot be 0 as these exponentials are not equal. So the only possibility is that C1 has to be 0. That is bad news, since it implies that C2 equal to minus C1, which should also be 0, and hence the wave function becomes 0. A zero wave function is not acceptable since it tells us that there is no possibility to find the particle anywhere. We encountered this issue because of the initial assumption that energy is negative. Apparently, the energy cannot be negative, and this can be understood from the fact that for this particle, the energy is all kinetic energy.
The classical physics say that the kinetic energy cannot be negative because it is proportional to the square of the velocity.
Now you see that the quantum mechanics agrees that the kinetic energy cannot be negative, but because of a different reason, it says like because of the boundary conditions on the wave function. Next, let's assume that the energy is 0. In this case, the solution of the ordinary differential equation is C1 plus C2x. Again, we apply the boundary condition. The boundary condition that psi equal to 0 at x equal to 0 now demands that C1 must be 0. The second boundary condition that psi equal to 0 at x is equal to Lx gives us 0 plus C2 Lx equal to 0. Since C1 we have seen it is already 0, so C2 must be 0. Once again we ended up in a situation where there is no non-zero solution. So the assumption that energy can be 0 must be wrong too. Note that classically it is perfectly okay for energy to be 0. It would simply mean that the particle is sitting in the box at complete rest. But in quantum mechanics, 0 kinetic energy is not acceptable, and it all has to do with the Heisenberg's uncertainty principle. Since the particle is restricted inside the box, its position is constrained, and so the uncertainty principle requires that the linear momentum must be uncertain. Uncertain momentum cannot be a zero momentum. What we mean by uncertainty is that the measurements will show a range of values for the momentum of the particle. So it implies that it is in motion and therefore it has some kinetic energy. Let's now try the only possibility left with us. The energy E is positive. In this case, the solution to the differential equation will be of this form: C1 cos kx plus C2 sin kx, with k defined as square root of 2me by h cross. There is no negative sign since we assume positive energy here. Once again we apply the boundary conditions. The boundary condition that psi equal to 0 at x is equal to 0 now demands that C1 must be 0. The second boundary condition that psi is equal to 0 at x is equal to Lx gives us 0 plus C2 sin KLx equal to 0. So this equation can be satisfied if sin KLx is 0 instead of C2. So you know that a sine function is 0 when its argument equals to 0, pi, 2 pi, 3 pi, etc. That means this equation can be satisfied when the argument in this function KLx becomes n pi, where n is 1, 2, 3, etc. So there is a non-zero solution for each of these values of positive constant k. So the wave function of the particle trapped inside the box must be C2 sin n pi x by Lx. You can see that this wave function is 0 when x is equal to 0 and also when x is equal to Lx. Also, the substitution of this solution into the ordinary differential equation shows that it satisfies this equation. Since the wave function depends on the integer number n, Each possible value of n gives one solution. So different solutions of psi will be distinguished by giving them a numeric subscript small n. That is, we write the wave function as psi n equal to C2 sine n pi x by Lx with n equal to 1, 2, 3, etc. having integer values. So one thing you have to note here is that n equal to 0 is not acceptable here. When n equal to 0, this means this argument will become 0. So this sign of 0 will be 0. Then the wave function itself goes to 0. It will be 0 everywhere. If the wave function were 0 everywhere, it means that the probability of finding the particle even inside the box is 0. This is not an acceptable situation because it means that there is no particle inside the box. So n equal to 0 is not an condition. Here n starts from, it has only positive integer values. Now, what is the energy of the particle? For this, we consider the relation between the constant k and energy. Remember, k square was defined as 2me by h cross. But just now we have seen that the values of k are restricted by the boundary condition, and k square must have only these values, n square pi square by Lx square. From these expressions, we get the required expression for the energy of the particle as n square pi square h cross square by 2m Lx square. We use this subscript n as energy is different for different values of this number n. We have a bit more work left with. You can see that the expression for wave function has a constant C2 in it. We have to know what value is possible for this constant. For that, we now try to normalize the wave function. We know that the total probability of finding the particle integrated over all possible positions must be 1. So the normalization process ensures this condition. So we have the condition that its norm must be 1. Ideally, we have to integrate the wave function from minus infinity to plus infinity. But for a specific problem, like the case of a particle trapped inside a box, we know there exists the probability of finding the particle only inside the box. So we need to integrate these wave functions psi from the left boundary to the right boundary of the box. That is from 0 to Lx. So we have the equation like this, in which we integrate psi n from x is equal to 0 to x is equal to Lx. So if you substitute for the wave function, we have an expression like this one. Now this is a simple integral and you can do that. If you do it, you get C2 as square root of 2 by Lx. So hence you obtain the required value for C. It cannot have any arbitrary constant values. It's a constant, but its value is determined by the length of the box. Hence, the normalized wave function of the particle trapped inside the box can be written as square root of 2 by Lx into sine n pi x by Lx with n having positive integer values. In summary, when the motion of particle is constrained inside a one-dimensional box, there is not just one energy eigenfunction and corresponding eigenvalue, but it has an infinite set of eigenfunctions and eigenvalues. And this constant in this expression is called a quantum number.